Hello, I'm Michael Fu with my co-author Claude Tenditentavon. We present our work, LineVul, a transformer-based line-level vulnerability prediction. So let me first introduce challenge in software vulnerability detection. So software vulnerabilities are costly and prevalent, but it's really hard to detect and prevent. Therefore, static analysis tools have been proposed, but they're still inaccurate. So we can imagine that within a project consists of million lines of code, security analysts may spend a huge amount of time to locate the exact vulnerabilities. Therefore, AI-based vulnerability prediction model have been proposed recently. Basically, it's a model to predict if a source code function is vulnerable function or not. So here's an example workflow. Given a code function, we first transform into vector space, which are numeric values. We then input into machine learning or deep learning model to predict if this function is vulnerable or it's a clean function. With this kind of approach, the security analysts are able to locate which function is a potential vulnerable candidate. However, a function can be really big and consist many lines of code. Therefore, security analysts may still need to inspect a big function. So recently, IVDetect, a state-of-the-art fine-grained vulnerability prediction, have been proposed. Basically, it's a function-level vulnerability prediction model plus a model interpretation approach. So given a vulnerable prediction, we input to an explainer. The explainer then interpret the original prediction model, then derive the subgraph level localization. Now, with this approach, security analysts are able to locate which part of a function is a potential vulnerable part. So here is an example of subgraph level prediction generated by IVDetect. We can see here, line 228, line 230 to 232 are treated as a vulnerable pattern by IVDetect. However, in this case, only 232 is vulnerable. Therefore, the security analysts still need to investigate the whole subgraph to locate the exact vulnerable line. We found three limitations of IVDetect approach. First, IVDetect only trained on project-specific data. Second, the RNN-based feature extractor of IVDetect is not effective to capture long-term dependency of a sequence. Those two limitations could lead to inaccurate vulnerability predictions. Last but not least, the subgraph level vulnerability localization is still coarse-grained, meaning more effort of manual inspection from security analysts. Therefore, we propose LineVul, a transformer-based prediction. So given a code function, we first subword tokenize into subword tokens, and then we transform into vector space. We then input to a 12-layer transformer encoders, which consists of a bidirectional multi-head self-attention followed by feed-forward neural network. The model then output two different things. First, the model predicts whether this function is vulnerable or clean. Given a vulnerable prediction, the model then output token attention score. We then summarize into line attention score and rank those lines to get the line level localization. Let me give you an example of line level prediction generated by LineVul. In this case, we can see that LineVul assign an attention score for each line. However, in this case, the line 232 has the maximum attention score, which is the exact vulnerable line in our case. Therefore, security analyst is able to locate the exact vulnerable line instead of reading the whole subgraph. Here's our study design. We aim to help security analysts to locate the vulnerabilities with less effort of manual code inspection. With this purpose in mind, we designed three minor objectives. First, we evaluate the accuracy of LineVul on function-level vulnerability prediction. Second, we evaluate the accuracy of LineVul on line-level prediction. Third, we evaluate the cost-effectiveness of LineVul on line-level predictions. To answer these three questions, we use empirical evaluation. For research question 1, how accurate is our LineVul for function-level vulnerability predictions? We found that our LineVul achieves the highest F1 measure, precision, and recall when comparing with other baseline models, including the SOTA IVDetect. We can also see a significant improvement over IVDetect here in F1 measure. Research question 2. How accurate is our LineVul for line-level vulnerability localization? To answer this question, we use two different metrics, top K accuracy with initial false alarm. With these two metrics, we aim to measure the line-level precision of different model interpretation approach. We found that the attention score reasoning of LineVul achieves the best top 10 accuracy and IFA when comparing with other model interpretation approach. So IFA, the lower, the better. So LineVul is actually the best. For research question 3, what is the cost effectiveness of LineVul for line-level vulnerability localization? To answer this question, we use effort at K% recall and recall at K% lines of code. We aim to measure the line-level cost effectiveness of the model interpretation approach. So we found that the attention score reasoning of LineVul achieves the best effort at 20% recall and recall at 1% lines of code when comparing with other model interpretation approach. So given a fixed amount of vulnerabilities, LineVul used the least effort to capture those vulnerabilities. Given a fixed amount of effort, LineVul can achieve the best accuracy of 24%. So some takeaway messages. Vulnerability prediction model is needed to mitigate the challenge of vulnerability detection and help security analysts to locate the vulnerable code faster. Second, LineVul is one of the important advancements toward more accurate and finer-grained vulnerability prediction. Thank you very much for listening. I recommend you to read our full paper because there are some technical detail that I can cover in this short talk. To replicate our LineVul approach, please go to our GitHub repository. For any issues or collaboration, please email this address. Thank you very much.
Thank you very much, Michael.